Thank you for joining us today. Today we have Charline, who is a PhD student at the University of Oxford and supervised by Marc Bellemare, Yi Wei-Ti, and Shimon Watson. Most of her work has focused on representation learning in reinforcement learning. Her long-term goal is to build agents that can learn over long periods of time. She has spent some time at Google Brain and DeepMind doing a PhD, and before that, she studied statistics at Imperial College London and mathematics at École Centrale Paris. And today, her presentation is on a recent work on the generalization of representations in reinforcement learning, which was one of the most highly requested paper on our discussion board. So we're really excited to have you here today, Charline. Please we're looking forward to the presentation. Thank you.
Thank you so much for the very kind introduction. And yes, I'm very excited to be here and to talk today about our work entitled On the Generalization of Representations in Reinforcement Learning, which was a paper accepted at ASAS last year, and for which I was very lucky to work on with Stephen from Google Brain, Adam from McGill, and Rishabh and Marc from Google Brain. It was also the result of valuable discussions with lots of other researchers that I would also like to acknowledge. And this talk is going to be divided into three main parts. So first, I'll present a theoretical characterization of the generalization of arbitrary state features. Then I will specialize our analysis to the study of the successor representation, which is an example of a representation that has been used a lot in the literature. And finally, we will look at representations induced by several deep neural agents and show how our theory explains the behavior of representations induced by deep neural networks and how it can help improve the performance of some existing algorithms in the offline setting. And feel free to interrupt during the presentation if you have a question or if you want me to clarify anything. I would be very happy to. Okay, so as you know, in RL, we are often dealing with systems with large or continuous states, which are encoded in an unstructured way. And we are typically interested in some type of value function that we can use to control the behavior of the agent. And because we cannot represent the value of each state, we need some type of function approximation to make accurate predictions on the basis of limited samples and estimate the value function. And to do so, what we can do is to learn state representations, mapping states to a representation, and to be able to generalize to newly encountered states. So here, if I take some examples of the example of the Atari games, what you would like to do is to generalize to the states on the left for these two particular games, to the states on the right. And so today, the method of choice to do so is deep learning. And so in DeepRL, what you do is that you start with these raw inputs. So for instance, these Atari frames that are coming from a simulator. And you feed this through some deep neural networks. So for instance, the DQN architecture, which consists of these three convolutional layers, followed by two fully connected layers. And these eventually become prediction of the value function, or like the policy telling the agent what action it should take in a given state. And what we call representation in DeepRL is all these stacks of layers, which are after the image, but before the actual prediction. So this would correspond to the layer here in red. This can be represented as like a k-dimensional feature vector for each state. And we also know pretty well by now that it's actually possible to control how these intermediate layers operate, and that actually has a lot of impact on the quality of the agent and the policy that we have. And it's also generally believed that auxiliary tasks which are known to improve the performance in DeepRL, play actually an important role in shaping this learned representation, state representation, right? And so this really motivates the need to theoretically characterize what does it mean for a representation to generalize in RL. And to answer this question, we will try to understand in this talk how representation learning impacts policy evaluation. So a good theoretical setting to look at is batch Monte Carlo policy evaluation. So it obviates some of the technical challenges in analyzing iterative methods such as TD learning, but as you will see later in the talk, it still allows us to provide some very practically relevant theoretical guarantees. So more concretely, we are given a sample of training examples, which consists of n pairs of states Si, and realization of the random return yi from Si, from the state Si. And so to simplify the math in the talk, we're going to assume that the states Si are drawn uniformly at random from the state space, but this can be generalized to other distributions. And the result that I'm going to present to you actually applies beyond reinforcement learning. So you can think of the setting as just being a supervised learning problem where you observe some states and the labels yi, which are, as I mentioned in our case, just like a noisy version of the true value for a fixed policy. And now, given these n pairs of training examples, what we'd like to do is to learn a good linear approximation to the value function vpi on the basis of these n pairs. So what we want to do is to map any given state representation phi of s, which is just this k-dimensional vector for each state, to its label y in a nice way. And our goal is to build this model such that it makes minimal error on some unseen states. So for instance, let's say here you are in blue, you have this the set of training examples, and in black you have some unseen states. And what you like to do is learn a model which performs well on some unseen states. Here the black states. And so the way we're going to measure this, the quality of this v phi w, so a linear approximate of the value function, is by using what's called in statistical learning theory the population risk, and which is in our case just the expected squared error loss, which basically just measures the difference between the prediction that we make under a model v phi w and the actual true label y. And now what we're going to do is to learn a k-dimensional weight vector hat w based on this n pairs of training data that we received and an empirical version of this expected squared error. And so what you're doing is you're just solving a least square problem to learn your hat w from the data. And so now one natural question that comes out of this is how well are we doing? So we have this training data, we are learning this hat w, so this weight based on this training data. How well is this weight vector going to do on some unseen states? And so yes, we'd like to compare this hat w that we learned from the data to the best we could do. And there are several options to actually measure what the best is. So the first option is to consider the optimal choice, which is like the true value function. So this is like the minimizer of the population risk that I introduced in the previous slide, but it might not be in the linear function class that we are interested in. And so that's why the other natural choice is to consider what's called best in class. So it means if we had infinite training data, what is the best hat w that I could choose on the actual population risks that we are evaluating on? And so now we can measure our performance by the difference between the risk of our linear model and the risk of the optimal choice, V pi. And this is what's called in statistical learning theory excess risk. And that will be denoted by this MATCAL E in the rest of the talk. And this excess risk can actually be divided in between two terms through this identity. So the term on the right can be sort of at the approximation error. So it means even if we had infinite data, infinite training data, there's still going to be a difference in the performance achievable between the model, which might not be between the model, and the true value function, which might not be linear, right? And the other term on the left is what's called estimation error. And it measures the problem of the lack of data, lack of training data. So we don't have infinite data. And so there's going to be a difference between what we can learn from really finite samples and the best in class, which corresponds to having access to infinite data. And so hopefully this estimation error term goes to 0 as the number n of training example increases to infinity. And now if we fix, so in this talk, we're going to consider an L2 loss. So basically the approximation error can be returned a bit more concisely as through like the orthogonal projection of the true value function on the column space of phi. But yeah, it's not super important. And yes, so given a fixed number of training samples, if we were to plot the excess risk, the estimation error, and the approximation error, we would get a plot which look a bit like this one that I drew. So it means that given a fixed set of data, if you increase the number of features, then your model is more expressive. But we don't have enough data to fit that model right, and we have low approximation error. So basically, if you have like few features, your representation power is pretty limited, and your model is less expressive, and we're not necessarily able to capture the true value function necessarily. But on the other hand, if you have more features, we indeed more expressive, and the approximation error is as a result going down. But we've increased the complexity of the model, and this might require a lot more data to be able to overcome these additional features that we're adding. And as a result, we might end up with a very large estimation error. And so we really need to find, in general, a balance here in the middle between to have like between estimation and approximation error. There may be like some questions, like this was mainly me presenting the background, but before we move on to like the actual contributions of the paper, I'm happy to make a pause and take some questions if there are some.
Yeah, I had one. By the way, I raised my hand on the thing. I don't know if you see. Just for looking if people have questions, you can see on the right side there is like a little raised hand. But my question was about the excess risk and the fact that like you use the best-in-class estimator. Doesn't this assume that you have this perfect neural network that can get you to that end up last layer of weights that decompose linearly? Because I was just thinking of like this other paper that came out recently, like that's about investigating the property of neural networks for representations. And they were saying that, for example, the ReLU activation function can be an issue and can are not as good as this other type of activation function. And that could cause maybe like, basically my question is best in class, but it looks like it's also saying that the neural network will be able to find this optimum last layer of weight, which I don't know if it's always the case.
Right. Yeah, thanks for the question. So I think so here I was like just presenting, like I wasn't even thinking yet about like neural networks. I was just thinking of like a linear like function class. and the reason we're taking this model in DeepMind is that because you can think of like in general you have your value function parameterized by like weights, and you optimize everything like jointly basically, but you can think it as an optimization problem at the two-part optimization problem, where you first optimize like the weights corresponding to what we call representation, so all this stack of layers, and then like this last layer which corresponds to the W here in the nodes. But I guess, yeah, if you were to think of like this linear, like best in class, it would, I guess, assume that you have like infinite somehow capacity, and that you're able to, with infinite data, to fit an infinite capacity to fit the model perfectly.
Oh, I see. Yeah, and that makes sense. And basically, like you take the assumption right now of, that like you just have a linear regression problem that you can solve optimally, basically.
Yeah,
and
exactly.
Don't care about the okay. Yeah. Okay. Thanks for that. And okay, one more. Just to squeeze one more. Could you re-explain why it's a trade-off between the two?
Sure. Yes. So yes, I was. So here, basically, when you increase the number of features, then you have more capacity and more expressivity for your model, and then the approximation error as a result decreases, because you're able to capture the true value function better, thanks to these additional features. But on the other hand, because here, like I'm considering a fixed number for this plot, the number of training examples n is fixed. It means that if you have additional features and a fixed number of data, you have some additional complexity that you are not necessarily able to capture from this finite number of samples, and as a consequence, the estimation error increases.
Oh, okay, I see. So it's like a variance and bias trade-off.
Exactly, that's
the variance decreases, but you get bias because you have a finite capacity and a finite data. So you start to overfit to the noise, and that's where like because you assume noise in your reward, right? And
yeah,
I think that's in the paper. Okay.
Yeah.
Okay, and that makes sense. Cheers.
Thanks. Yeah. And by the way, I can't see like the screen of like the Microsoft team, so I don't see the questions. So just interrupt me if you have questions, because I can't see them.
Oh, okay. Then
might be very.
Yeah. Sorry, Lucas, you want to say something?
Sorry, yeah, a brief question on this plot. So, from my understanding, if you would increase the data points that you get for this particular plot, effectively the red line would just slowly flatten out, right?
Yeah.
The more data I have, the more that goes, and that also means that the more data I have, the less the increases in the excess risk towards the end of the slope, right?
Yes, that's correct.
Okay, perfect.
Yeah, because we got a few people on the call, I would say the best is like, guys, still raise your hands if you want to have a question, and then I will moderate. I'll just interrupt and do the bottleneck basically. Yeah, please go ahead, Charline.
Cool. So we found that a key notion which was driving the generalization to unseen states is what we called the effective dimension of a representation. So the effective dimension of this representation phi, which is just this number of states times number of feature matrix, can be used to bound the excess risk of least square regression applied to a particular state representation phi. And it determines how many samples are needed to obtain good generalization of the value function with a fixed chosen representation. So it means that it dictates the number of samples which are required to achieve low estimation error. And it measures the degree to which knowing the value at one state informs the value at other states. And so more formally, it is defined as the number of states times the maximum over all the states of the L2 norm of the orthogonal projection of each basis vector onto the column space of the representation phi. So let's maybe take an example to get some intuition about it. So if you consider, for instance, the case of a representation phi where basically all the columns have unit norm and are orthogonal with each other. We have a simplification of like this projection matrix, can just be expressed as like representation times representation transpose. And if you were then to write down the effective dimension, you end up with like the maximum of over all the states of the L2 norm of the feature vector at each state. So if phi is your representation matrix, number of states times number of features, it's like the maximum norm of all the rows between all the rows of this matrix. And intuitively, this effective dimension really measures the lack of sparsity of like the column space of your representation. So yeah, and in the best case scenario, this effective dimension is going to be equal to the number of features. And in the worst case scenario, so it means when you're not generalizing at all, then it is equal to the number of states. So if I take an example, so here I'm taking a one-dimensional representation. So this is just the number of states, and you have like one feature for each state, which is 1 in the first state and 0 everywhere. And then you can show that the effective dimension is here going to be equal to S. So you in the worst case scenario. But on the other hand, if you were to have like the same value for between all the states, so your feature is the same between all the states, then this is equal to like the rank of the representation. So here, like let's say it's K, and it's like because it's full rank. So this corresponds to like the base case scenario. So this vector full of ones is really desirable. Yeah. And yes, what's really nice also about the effective dimension is that it's really a property. It means it's a property of the subspace spanned by your features. So it means that if you have two representations, so two matrices phi 1 and phi 2, that span the same subspace, then they will have the same effective dimension. And there's also like a relationship between the effective dimension and the notion of coherence, which appeared in the problem of matrix completion through this identity. So then this coherence and the compressed sensing literature is used to characterize the feasibility of low-rank matrix recovery. So in some sense, like this generalization problem, when you want to generalize to new states, so new rows in your representation matrix, it can also be thought of as a kind of a matrix recovery problem, matrix completion, and that's why this kind of same notion appears in our case as well. Okay, and so here is like the main. Now we have I have introduced this tool to which enables me to show you the main result of the paper, which is a bound, which characterizes the excess risks that I introduced earlier as of the linear approximate model V phi W hat, and this bound applies to any stage representation. And it quantifies the natural tension between like representations that generalize well, so having low estimation error, and representation that approximate well, so which have low estimation error. So here you have like the first term here, which corresponds to the approximation error. And so it reflects the error due to the fact that we are using this k-dimensional linear approximation. And the remainder of the bound is basically the estimation error. And the theorem here demonstrates that the ability of a representation to generalize is quantified not only by this approximation error, but also that appears again in the estimation error part of the bound, but also on this effective dimension. It appears in the bound here, but it also appears in the top. So he dictates the minimal number of samples which are needed to obtain a high probability bound. So it means when the effective dimension is small, then the bound will hold for fewer samples. Right. And yeah, so I think, and this bound is, the proof for this bound is based on concentration inequalities. And so you end up with a bound which is sharp in the sense that you have a bound in 1 over n. Yeah, and I don't know if you have like questions about like the theory, but the rest of the talk is going to be about demonstrating the usefulness of this bound by looking at specific examples like the properties of the successor representation. So maybe hopefully like you will get more intuition about it and understand why like this effective dimension is useful in the rest of the talk. But if you have some questions before that, I'm happy to take some.
I don't see any questions, so I think yeah.
Okay.
Yeah.
Cool. So yes, so now I'm going to show you which structure of MDP leads to good generalization for the successor representation. The successor representation is an example of a representation which has been used a lot in the literature, for instance, in exploration, option discovery, and neuroscience. And now we demonstrate that the effective dimension plays an important role in determining the representation capacity, the generalization capacity of representations derived from the successor of representation. And then I'm going to show you some environments with a particular transition structure such that the best case scenario where the effective dimension is equal to the number of features is achieved. So just to be sure we're on the same page, with the successor representation, we're not really interested in proximity in space, but rather proximity in time. And so it's defined with respect to a fixed policy. And given a start state S and a given state S prime, it is defined as the expected discounted sum of future occupancies at S prime if you were to start the process at S. And it's also the value function at S if the reward is 1 at S prime and 0 everywhere else. And it can be expressed in matrix form as this psi pi matrix, which is number of states times number of states. And then it's just equal to identity minus gamma p pi inverse. And one of the nice properties of the successor representation is that you can express the value function. So here it's just a vector of size number of states as a product between the successor representation matrix and a reward vector. So this is a reward vector of size number of states. And so we're going to consider the state representation constructed from the top K left singular. So if you write the singular value decomposition of the successor representation, we're going to consider the representation which is given by the top K left singular vectors of the successor representation. So this would correspond to the FK here. Also, if you if you also write down the approximation error for given this particular representation, then you end up with the approximation error, which is really a function of the singular values of the successor representation. So it's just because we're going to look at the decay of the singular values of this representation, and yes, this is really a way to characterize the approximation error. So we're going to look at 5 different graphs. So the first one is a disconnected graph. So each state is basically isolated from each other. Then we have a fully connected graph, a star graph, an open room, and a 2D torus. And we're going to basically consider this graph and a random walk induced on these graphs. And this is going to lead to a transition matrix with a particular structure. And empirically, we find that the effective dimension of this representation and therefore its generalization characteristics can vary a lot according to the transition structure of the environment. So yeah, for instance, here we consider, if we consider these 5 graphical structure with like we have 400 states for each of this structure. And here we're going to increase the number of features of your representation. So K, like if you represent your representation as like a number of states times K is the number of features. It goes from like 1 up to 400. Yeah, you can see here that there are basically 3 different kinds of spectra on the left if you look at the decay of the singular values of the successor representation. You have the fully connected and the star structures, which have a very flat spectrum, both with like an important first component, but the last one, which is like much smaller in the case of like the star structure. And on the other hand, you have the grid and the torus, which have a very decaying spectrum. So it means that to have low approximation error, you might need a lot more features. And on the right, we are here looking at the effective dimension of these representations as a function of the number of features. So you can see that both the star and the fully connected graphs have a very high effective dimension, although they have like simple structure. On the other hand, what's maybe surprising is that the open room and the torus, they have like visually very similar structure, and like the spectrum on the left was the same, but in terms of approximation error, there's like a big difference, and the torus really performs better, and this torus achieves like the lower bounds. So the best case scenario where the effective dimension is equal to the number of features. So surprisingly, like the torus is really like the structure for the successor representation, leading to the best in terms of generalization. Here I'm also trying. We are basically plotting empirically the excess risk, and on the right we are plotting our bound. We also see like that the torus achieves like a low excess risk overall, and achieves better than the open room, which is also captured by our bound, basically. Yeah, I think that's mainly it for that. Are there some questions about this experiment?
Yes, I had one actually. You know, when you, or more like an observation, I wanted to know what you thought about that. I would almost argue like the grid structure is more complex than the torus structure because you need more rules to explain the structure of the room structure. In the torus, it's like a proper convolution that is cyclic.
Yeah, each state has like 4 neighbors, so like in terms also maybe in terms of like mixing time, like it's easier to diffuse maybe somehow.
Yeah, I felt it's maybe more edges, but simpler structure. Even if to us it's not simple because we're used to things ending somewhere.
Right. Yeah.
And also I had another question on when you go back a couple slides, it really looked like an eigenvalue decomposition, but it's not, right? It's because it's like not a square matrix. It's just like it fills especially in the paper, like you know, you have this diagonal matrix with the sigmas. It looks like eigenvalues to me a bit. So is there a link there or not at all?
Yeah, so like the psi matrix is actually squared, so it's states by states matrix. But the thing is that it might not be symmetric. And so like again, the eigen decomposition is in general different from like the singular value decomposition, except if the matrix is symmetric.
All right, okay, thanks.
Yeah, and so yeah, the approximation error is really related to the notion of SVD and not about the eigen decomposition.
Yeah, I guess it's more general that applies also to non-symmetric.
Yeah, and also like if you do eigen decomposition of an arbitrary matrix, you might not have like it might not always be diagonalizable. So sometimes you can have some complex eigenvalues in the sigma, like the matrix in the center, and sometimes it's not even diagonalizable. While if you work with the ADD, you always guarantee to have any matrix has a singular value decomposition and with real entries for each of the matrices as well.
Okay, thanks a lot.
Thanks for the question. Cool. So now we are going to look at the second experiment where we are interested in comparing the generalization capacity of different representations, because one of our motivating questions of this project is really which representations generalize well in RL. So we're going to compare the successor representation in blue to other theoretically motivated representations. So for instance, like the bisimulation, which is a metric which captures the behavioral equivalence between states and depends on both the reward and the transition structure, while the successor representation is independent of the reward function. And also the Krylov basis, which is generated by like p-pi and the reward, and finally some random features. And so we're comparing them both in terms of empirical excess risk and effective dimension, and as a function of the approximation error. We are interested in here we are looking only at the four-room domain because which is depicted at the top, and the setting is really similar to the graph experiment that I just presented. So we have the reward, which is a one hot vector, and we are basically doing the same kind of experiment as previously, these results really show that the effective dimension plays an important role in determining the usefulness of a representation, because for a fixed approximation error, a better effective dimension corresponds to a better excess risk in some sense. So the successor representation, for instance, it generalizes well, basically, but it has worse approximation error compared to the Krylov basis, so the bisimulation metric, which take into account the reward. But for small approximation errors, the Krylov basis has smaller effective dimension and is performing best. And finally, the random features, which are agnostic to the structure of the MDP, have very high approximation error, which is intuitive and really makes them unappealing in some sense. Right. And finally, we're going to look at some deeper experiments. So we're going to do an empirical study on the archive learning environment. And we find that the notion of effective dimension really correlates with other empirical performance of existing value-based deep RL agents. So here, for instance, I'm reporting on the right the performance of 5 deep RL agents, so DQN with Adam as the optimizer, Rainbow, DQN in its nature version, IQN, and IMA-IQN. So here, like we can see the performance on the right, and on the left, we are reporting the effective dimension of the representation, so the penultimate layers induced by these 5 agents throughout training. So we are really not optimizing anything. We're just like taking the representation, the penultimate layers of the networks throughout training and computing the effective dimension. And so you can, and we're also taking a very large batch size to compute an approximate of the effective dimension. So basically the representation is going to be large batch size times number of features. So we can really see a strong correlation between the effective dimension of the representations and the performance of these different agents. So this really suggests that the effective dimension and thus like the generalization plays really an important role in the performance of these online agents, which is maybe like a surprising in some sense. And we can also notice that starting from iteration like 50, the effective dimension increases. So this suggests that there might be some overfitting of the representation to the current value function. And this is also an observation that has been made by Will Dabney in a paper called The Value Improvement Path. So this is in line with this result. So showing that, yeah, starting from training, like we are overfitting maybe to the current value function, and this is why, in terms of effective dimension, it's getting worse. While like before, it was like actually decreasing. And yeah, now was the last experiment to really further corroborate the claim that low effective dimension corresponds to better generalization. We're going to try, in some sense, to minimize, to add an auxiliary loss inspired by the effective dimension, and to try to minimize this auxiliary loss. So trying to minimize this effective dimension throughout training to get better generalization. And so here we're going to focus on the offline setting, because we want to avoid confining factors like exploration with online agents. So here, like this loss is like a smooth version of like a max, the max which appeared in the definition of the effective dimension. And so we added this auxiliary loss on top of the Acuan agent. And yeah, we found that actually, like if we're plotting on the left the effective dimension throughout training, and on the right we are looking at the performance of these two agents, like overall, when we added the auxiliary loss, this resulted into better performance of the agent. Although we can see that it's only really at the beginning of training that the effective dimension was lower for this agent compared to like the baseline. So yeah, I guess it's yeah, it's hard to really disentangle in some sense between approximation and estimation error effects. So probably like there needs to be further study to understand this phenomenon, trying to understand whether like generalization is more important at early on in training, and later it's approximation, or trying to understand something like that. But yeah, it seems like trying to minimize this kind of loss overall results in better performance. Yeah, and that's mainly it. And thank you so much for listening, and I'm very happy to take any questions if you have some, and discuss further some of the material.